directly that couple right to robotic motors, or you go the other side of things and you go buy a drill and whatever motor and you do the work to couple them together. But basically the gear ratio on these for an even set where the sun is the same as the planet is the ring gear divided by the sun gear plus 1. Yes?
But the Roomba wheels about the same. With the Planetary.
I've never hacked apart a Roomba. I don't know.
Okay.
But Planetary gearboxes are relatively common. I mean, essentially, if you ever encounter a gearbox where your motor is directly in line with your output shaft, it's probably a Planetary gearbox. Every other type of transmission, your motor is going to be offset from your output shaft by some degree. So that's the number one way to tell if it's a Planetary. A drill, the motor's right behind the driver. Similar to, so if you take apart any robot and you see that, that's going to be your indicator you've got a Planetary gear set. And essentially the other part of it, it's got a great efficiency because they're spur gears. I mean, that's what they are. They're just transferring it one level to another, but they are spur gears. Now the more you have in a system, the decrease of efficiency goes, but Planetary transmissions are great. Yep.
I was just wondering if you heard of harmonic gear drives.
I have heard of harmonic gear drives.
Yeah.
Harmonic gear drives are, okay, I'm trying to think the best way to describe it. You want to jump in, or you just want to?
No, I just.
Basically, harmonic gear drives are the inner ring is not. It basically flexes. So,
I think it kind of wobbles like it.
It basically you're looking at a gear that's not round, and by moving around in an elliptical fashion on the inside of a ring gear, you end up with an extreme reduction in a very small amount of space. I've never built one. I've never used them.
I hear it's also pretty efficient too.
But it is because it's a single reduction.
Yeah.
I mean, when it comes to gear trains, the less amount of reductions you have, the more efficient the drive is going to be. The more steps between what your motor is and what your gear is, you're going to lose power at every step, and that's due to heat and misalignment. And
those are used in large humanoids. That's the main purpose for the last drive train.
Okay.
5-foot, 6-foot humanoid.
I've seen some small ones, but I've never really found an application to use it over some of the other ones. I mean, this is basically what I've presented is kind of, I wouldn't say the order of my preference, but I always try to stay in the spur gear chain drive world if I can do it. And then you start introducing the other types of gear trains if you have to. Mostly that's because anybody in this room can build a spur gear drivetrain or a chain drive. You start getting into Planetary gearboxes, bevel gearboxes, worm gearboxes, Planetaries. You kind of step beyond of the realm of the average person to build one from scratch. But there are plenty of commercially available ones, so it kind of all depends. This is a gearing example of how to go basically from a motor to a wheel and the calculation steps involved. I probably should have walked through this example in my slide, but basically you have a gear 1 to gear 2, and gear 2 is on the same shaft as gear 3. So you've got one stage of your reduction, and then the speed of this gear is the same as the output speed of N2, and then now you have another gear reduction. So in terms, they multiply. So you do your first stage reduction, and if you share a common shaft with a separate gear train, you essentially multiply the gear ratio to get the final speed. Now, there is one consideration with this as far as a wheel goes. And ultimately, in drivetrain, it's all about how fast you're actually going to go. You have to think of your wheel as a gear, because the change in diameter between the output shaft and the change in diameter will affect your speed from the perspective of your circumference is what you're actually looking at determining your speed. You have the RPM, which is always going to be the same, but your actual movement, how fast it's going to move, will be your wheel. And so if you go really big on a wheel, you're actually essentially gearing up by going larger, and you're scraping a lot of the work you've just done getting it down to low speed. I guess do people like me to walk through this, or is this a kind of a good just snapshot of it? I'm going to move on. So motor characteristics. The three motor characteristics that I look at, there are a lot more than this, but stall torque, it's the highest amount of torque a motor can generate, and the motor will stall at load. Stall basically means stopping. Basically becomes a giant heat sink at that point, because as a motor is spinning, it's dissipating heat into energy, and when it's not, well, all your amperage is turning into heat, and you'll cook your motor that way. And that's when you release the magic smoke. So stall current, it's the amount of current drawn when the motor is stalled. So that's a really good point for, you find a motor and you're not sure where you are, you don't have a motor curve. A great way to do is hold the shaft, take a current reading. You'll get the stall current. And you get the stall current and you get the free speed, and you can kind of figure out everything else in between. The great part of systems like this is that they're all relationships. So it's pretty straightforward. The last thing is free speed, and that's how fast your motor's going. You give it 12 volts, and it's just wheeling. Now obviously, DC motor world, the higher the voltage, the faster the motor's going to go. So when you're trying to determine what you don't know, pick a nominal voltage, and you'll figure out what your stall is for that motor in that scenario. So this is a standard motor curve. They all are going to look similar to this. They are not necessarily going to be this exact diagram. Based on different applications, they'll have different characteristics. So speed torque, obviously the same relationship we said. This is almost always a linear relationship. Well, it is a linear relationship. The higher the speed, the less torque. The more torque, maximum torque at zero speed, or zero torque at high speed. You can look at it like that. Your next one is your current versus torque. At free speed for a motor, your motor is going to be drawing the least amount of current. When you start to load it down to stall, that's when it's going to draw the most amount of current. So if you stall a motor and you're trying to spec out breakers for your system, figure out where you are at stall, that's where you should be. Now, the power curve is the combination of these two. It's bringing the time element into this. So what we always say to try to design for is trying to design to run in the top third of your power curve. There'll be a point where these curved lines will interact, and you want to kind of design to a point saying, look, you can also plot current on this. If you plot current, you're trying to stay in this first third of your power curve for optimal efficiency. But remember that power is absolute. You can move a car with a tiny motor, because any motor can create any amount of power. It's all about the time, or any amount of torque. It's all about the time. You can take a tiny motor and move a car. It might take you 100 years to move a millimeter because you have to gear it down so far, but theoretically you can do any amount. So it's all about how fast you can actually implement that torque. And then the last thing on my list here is traction, which is kind of okay, everyone knows what traction is. You get sticky wheels, you get slick wheels, you find what you could use. But the static versus dynamic frictional force is significantly different. When you have a stationary object and you push on it, it's a lot different than once you're already moving. So once you slip, the ability to slip more is more likely. So if you're in the BattleBots world, or in the in the competitive robotics world, where it's more of a teleoperated thing, if you're stationary and someone's pushing on you, you can resist a lot more force before you start moving than if you're moving. one of the things we always say is design encoders into your system at the front. It's really hard to censor things on the back end, and when you're trying to build a system that's possibly dynamic and be able to be reactive, whether it's a PID loop or elsewise, putting them in early in the system is good. And you can do stuff like dynamic braking with traction control, but you have to be able to track your wheel speed. And your pushing force, and this is one that I always get for competition robots, how do I know how hard my robot's going to push? Well, it has to do with your normal force, right, times, or your weight, times the coefficient of friction for whatever you're pushing on. Now, these are some generic coefficient of frictions for wheels with covers on carpet from the world, but you can also figure out your coefficient of friction for any scenario you happen to possibly be in. So you take a mass of a known mass and you pull it, and whatever the material interaction here, so if you're trying to do like a tread against a carpet, you want to see what your thing is, you load it up with weight, you pull it, you figure out what your force is that you had to pull it before it starts to move, you figure out what your weight is, and now you know what your mu is. So now you couple that with your weight, so now your robot weight times its normal force will be your pushing force, regardless of what your gear train is geared to, because the limiting factor is always going to be traction. You know, if you have more pushing force than you have traction, your wheels will start to spin when you get to that point. You know, you will lose traction on the ground. So this is where the full system engineering, you know, the full design system from a higher level comes in, where you say, look, these are my circumstances. These are the wheels I know I have. This is the environment I'm going to be doing. So this is about the pushing force I'll be able to do with the size of the robot. And then you can gear your motors accordingly so that you will never lose traction, which is a pretty novel thing. Now, not all of these rules are always applicable to all the robots that everybody builds in this room, but from a competitive robotics world, this stuff's the...
I point out that the normal force is not the weight of the robot.
Okay. It's the weight, okay. It's the supported load based on...
the weight on the wheels, on the drive wheels.
Yes. So what he's saying is that the scenario I've driven here is basically a four-wheel drive where all the wheels are driven. If your robot has two-wheel drives with two casters, half your weight, or depending on where your center of gravity is, may be supported by a non-driving wheel. Your normal force is cut in half. So if you have a, you know, a chair is a good example. Your weight is equally spread on those wheels. Now if you cut those legs off and the back was just floating in the air, all your weight's going to be on the front too, so your normal is the same. But if, oh, chair's a bad example. I'm going to backtrack here. This is where editing comes in. Basically, it's all about driving wheel, transferring wheel to the ground. So you want to have most of your weight over your driving wheels. If you are using a skid bot, putting your center of gravity over your wheels will be good, but you are going to be scraping the weight. So that's why I go for those six-wheel drive bases where you're always, all your wheels are moving. Thanks for the clarification. So kind of to wrap up, I have a couple tips, things to make building robot drivetrains easier. Buy stuff off the shelf if you can afford it, and you can. This will save so much time and energy in the end, but it all has to do with the budget of your project. Now, I'm a realist, and I know that sometimes you got to scrap together with what you have, in which case use the fundamentals and design systems that work as well as you can for what you've got. But if you can buy off-the-shelf components, there are plenty of sources out there, Vex, McMaster, Granger, BaneBots, Robot Marketplace, and go on and on about these different AndyMark that sell parts specifically for robots. And it makes it very easy. Chains and belts are very